Well, here's a short video segment to describe how we use Snell's law to find the index of refraction for some material. Snell's law is to refraction what the law of reflection is to reflection. So in the diagram that I've shown here on this page, we see what happens when an incident ray comes in from the upper left and strikes the boundary between two different media. The wave energy splits. Some of it goes off as a reflected ray, much like you would reflect off of a mirror. And of course the law of reflection is fairly simple, because as you can see there, the angle between the reflected ray and the normal is just equal to the angle between the incident ray and the normal. But the angle of the refracted ray is not so straightforward. It is related to the incident ray by a more complicated equation known as Snell's law. So I'm going to demonstrate how that works and how we can use it to calculate an index of refraction. In a separate video, I'll show you how we can use a known index of refraction to calculate an angle. So I have an example here of a diagram of a typical refraction situation. Got two different medium 1 and medium 2. I decided to call the upper one air because that's very typical of the problems that we do. The bottom one is some unknown material. It could be a glass or a plastic or even some kind of a liquid. I've decided not to draw in the reflected ray, although there would be some light reflected off of this boundary. That's just for some clarity. And I've decided on a couple of angles to label on this. Now I've done something to call your attention to how careful you need to be with the angles. Every time we do anything in optics, whether it's with reflection or with refraction, we always have to measure angles from a normal line. Sometimes the normal line will not even be drawn for you, and you're going to have to draw it yourself. In this case, we have a normal line drawn already, but the angle that's given in the medium 2 is not given from that normal. It's given from the boundary itself. So that 70 degrees is not going to do us any good when we go to use an equation. So we know that the entire angle between the normal line and the boundary must be 90. That's why we call it a normal line. And so that means this little refraction angle down here must be 20 degrees. So that's our situation. We have an incident ray striking the boundary at 50 degrees and a refracted ray at 20 degrees. We must know something about air, and this is something you could look up or just something that you can remember. But the index of refraction for air, and we use the symbol N, is 1.00. You can just use 3 digits on that and that's enough. So what we're going to do is find out what the index of refraction is for medium 2. So I'll just put N2 and that's going to be our question mark. Alright, so we're going to start by using Snell's law. Now you'll find Snell's law on your reference sheet. You can find lots of different versions of it. I think what I usually like to do is keep it kind of generic. And we write it index of refraction number 1 times the sine of the angle we call theta 1 is equal to the index of refraction we call N2, that's the other medium, times the sine of the angle we call theta 2. Theta is the Greek letter and it often is used to indicate an angle. So the key to this is to recognize that on one side of Snell's law equation you have an index of refraction and an angle that goes with it. So that can be either one of your two media. So I'm just going to use medium number 1 for that. You've got to make sure that you get the right angle for the right medium. So because we're dealing with air, we'll use 1.00 for that. And then you put in the sine of the angle. And the angle must be the angle that's being made inside the air. So that's the incident angle, and that's 50 degrees. And then on the other side, we have our unknown index of refraction N2 times the sine of the angle that we're making in that medium. And remember, that's going to be 20 degrees, not 70 degrees. Alright, then we're going to do a little algebra. Keep in mind we're looking for N2 there. So all I have to do is divide both sides by the sine of 20. So I'll get 1.00 times the sine of 50 divided by the sine of 20. And that will equal N2. So now it's time for your calculator. I'm going to caution you to make sure you close your parentheses properly. Just to emphasize where these go, I'll draw it in red. You have to put an open parenthesis right after the sine function. Now your calculator will do that for you, and then you'll close it after the 50, and similarly you're going to have to put parentheses around the angle 20. Shouldn't need any other parentheses in this particular situation. You also want to make sure that your calculator is in the right mode. It has to be in degree mode. If you're in a class where maybe you use radians, or maybe you don't even know what mode you're in, you're going to want to double check that by hitting the mode button or some other appropriate button on your calculator. But if you punch this in properly, you will get an index of refraction number of about 2.2. I want you to always do a little bit of a check. The check is something that you've already encountered in an earlier mop, and that is the higher the index of refraction, the more bent the ray is towards the normal. So it makes sense that because we are bending more towards the normal in medium 2, the medium 2 has to have a higher index of refraction than air. Of course, in the case of air, everything has to have a higher index of refraction because there's nothing with a lower index than that of air. So that enabled us to calculate the index of refraction. Very similar calculation can be done to solve for an angle. Let's say you know both the indices and you need the angle. But the math looks a little different, and I did make another video segment related to that shows some of the detail. But this should be enough to get you going on a lot of the problems. Any more help that you need on this, make sure you come and see me in the classroom.